Okay, so now we have learned that we can write regular expressions. The regular expressions can get translated or converted into an NFA, then the NFA gets converted into a DFA. The way we will be doing this is that we will be using a tool that will take regular expressions. So you will write a file that has regular expressions in it, and that file will have rules for the different syntactic categories in the language. So you will have RE for integers, RE for identifiers, RE for for example, floats.
Expressions.
No, so expressions are not. So the REs are for the words of the language, the syntactic categories. Now, we will be using these words when we get to parsing. We will be using these words to build sentences or statements. Then there will be REs for the different keywords. RE for for example, if, which is a trivial RE. RE for RE for while. So for the keywords, the RE for a keyword is the keyword itself, because it's a language that has a single string in it, which is that keyword. Then the union of all of these REs is going to be the set of REs for that programming language. So if you take the union of these REs, then you will get a big RE for the programming language. I think we are done with this. So when we use a scanner generator, when we have a scanner generator, that scanner generator takes REs and it gives us C code for the scanner. Or let's call it scanner code, regardless of the language. Scanner code. It takes the REs. We only define the REs. We only feed it with a file that has the REs for the different syntactic categories in the language. And it generates the scanner for us. And internally, it does that by converting this RE into an NFA. So it does, the Thompson construction, and it converts this into NFAs. Then it does the subset construction, and it converts this into DFA, or into a DFA. In fact, it's one NFA, because it's the union of many DFAs. Then it does some DFA minimization. In fact, this part we will not be studying this, so let me extend this. So scanner code, and so there are some algorithms for minimizing the DFA, minimizing the number of states in a DFA. So DFA minimization, and that gives you a minimal DFA. So is DFA minimization covered in 135? Is it covered?
Not in great detail.
Okay, but we will not cover it here because it's not an essential feature in theory. In practice, it's important, but it's in theory, it's not essential. What's essential is converting the REs to NFAs, then NFAs to DFAs, and this is a minimization. Then just then you generate code for the DFA. So this is code generator. So remember that this is not the compiler's code generator. All of this is only generating the scanner for us. Okay? So this is not the code generator of the scanner. This is only generating the scanner code. And the scanner code is going to be one of the many source files that constitute the compiler source code. So the scanner is only one stage in the compiler. So in the assignment, in the first programming assignment, you will be basically writing REs for some programming language, a basic programming language, and then you will be using a tool, which is Flex, to take your REs and construct scanner code, generate scanner code for you by doing this. So internally it does this. Now we understand what it does internally, except for this part. In fact, this part is the one that we'll talk about today, even though it's very straightforward. At least we know this and this. Okay? Now, so the point is, this subset construction is running while generating code for one part of the compiler. So we are generating, one source file in the compiler. This is what we are doing. So this is not done when we are compiling applications. This is done when we are building the compiler itself. Okay. So now let's now see the implementation issues that that we need to understand when it comes to building a scanner. So when you build the NFA that will get built will look like this. So this is a start state. Then you may have this, for example, for identifiers, you'll have 0 to Z. Let's ignore underscore, just. And then you will have this accept state. And in this accept state, you will loop, assuming that an identifier is, consists of, starts with an, this is A to Z. Starts with a number and followed by any combination of numbers and letters. So in this case here, we will have A to Z or 0 to 9. Okay? So this NFA will have an accept state for identifiers. So this is the identifier accept state. And it will have an accept state for numbers. So integers, it takes 0, 9, and then you have to have at least 1, and then 0, 9, assuming that we will, this is integers with leading zeros allowed. So this is an accept state for integers. Positive integers. And then you'll have states for the keywords. So you will have, for example, 4. This is for the 4 keyword. So this is the accept state for the 4 keyword. And each keyword can have its own branch of the NFA. Or you can think of this as the union of multiple NFAs. And you can have, for example, a new keyword. Okay. And you'll have a bunch of them. You'll have a bunch of REs for the different syntactic categories. So identifier is a syntactic category, integer is a syntactic category, and each keyword is a syntactic category by itself. Now when we recognize, so suppose that this is our input. X 1, 2, 3 equals 5, 59. So in this case, the scanner, this is an NFA, by the way. So this is an NFA. We will explain this assuming an NFA, but keeping in mind that it will get converted into a DFA. The NFA is easier to understand. It's probably easier, for humans because it's there are fewer states, while the corresponding DFA is going to have more states in it. So for us as humans, it's easier to work with the NFA, but we know that we can always convert it into a DFA. So in this case, the scanner will try to match this. So here, x12, so it's gonna take this path, and it will recognize. In fact, x is gonna lead to an accept state. So x itself will lead to an accept state. So now should the scanner just take this x as a valid token or keep scanning?
Should keep scanning.
Yeah, should keep scanning. So in this case, it will keep scanning until when?
It hits a different token or delimiter character.
But
That's
how
not
will
part of the regular expression.
So in fact, if you think about it as from language recognition point of view, it keeps going until it gets to this. And this lexeme, this doesn't match anything in this NFA. Right? There is nothing in this NFA that matches this with the equal sign. There is something that matches this, right? So up to this point, this matches an identifier, right? But when we read the next, then there will be no match. So basically, when we get here, with the x1, 2, 3, we are in this accept state, and the next symbol, which is the equal, there is no transition for equal here. So, or equal takes you to an error state. So if you get an equal, if there is no transition shown explicitly, this means that this is an error state or trap state. So the scanner will keep scanning until it hits an error like this. And it knows at that point that it will have to go back, roll back to the last accept. And in this case, the last accept is here, happened here. So it will take x12 as the first lexeme that it could match with the syntactic category. So it would say, okay, this lexeme is an identifier. And then we'll start over. So we'll just flush this, and we'll start scanning from this point. And this equal is going to match some NFA here for equal. So there will be a trivial NFA here for equal, and this will identify it as an assignment. Okay? And then, assignment, when it matches this with an assignment, there is no transition with a 5, with a number. So it will stop there, because it will not, equal 5 does not match anything, right? Equal 5 does not match anything. So when it gets to the 5, it knows that, okay, this is not going to match, so I will take the last match, which is the equal, and now I will start over, and I will try to match the 5. So the 5 is going to match here. With the 9, we will stay here, and if there are other numbers, it will stay in this accept state until we get to something that does not match, which is the semicolon here, so it will stop. It will take this as, so this is the assignment. This is an integer. And then it will match this as end of statement. Okay. So basically, in order for this to work, the scanner will have to go for the longest match, not the first match, the longest match. Now, this leads to a question of what will happen if we have multiple matches. So, can you think of a, given this example, can you think of a string that has multiple matches?
Yeah, 2 equals in succession.
2? 2 equals? Equal. No, let's stick to what we have here. So we have, with what we have in this example.
4?
Yeah, so 4. What if you have 4? So if you have 4, then 4 will match here, and it will match here. So there will be 2 accept states for 4.
Oh, okay.
Okay. So 4, again, we are looking at this as an NFA, but keep in mind that this will get converted to a DFA. Okay. So the corresponding DFA for this, let me just verify it. So if, let's call this N1, N2, N3, and let's call this N4. So the corresponding DFA only for the identifier and the 4, ignoring everything else, is going to be like this. We'll have a D0, then this will go to a state that corresponds, we will be either in N1 or N4. So this is going to be N1, 4, and is on an F. So will this be an accept state? Yes, it will be an accept state because 4 is an accept state, but 1 is not. So this will be an accept state. And with the O, we will go to state N24. So this is 2 and this is 4. And this is also an accept state. And then with the R, we'll go to state N34. So N14, it has only one accept state. So if we match here, this is only an identifier. But if we get here, then it's both identifier and 4 keyword. Okay, so now in this case, if we have multiple matches, so in fact, it's up to the person who's defining this by regular expressions. The scanner generator allows you to specify priorities, certain priorities. If you have multiple matches, which one should be taken? And of course, the logical thing here is what?
4.
Is to take the keyword. And the way you specify this, when you write the regular expressions, so in that file with regular expressions, so you write regular expression for the keyword before you write the regular expression for identifier, because the flex scanner generator takes priorities based on their order in the regular expression file, the file that has the regular expressions in it. If you mention keyword first, then you are saying that if you have multiple matches, then take the first match, or the one that appears first in the list of regular expressions. Okay? All right. But if you have a string like forecast equals 7, in this case you will not have multiple matches because you will go for the longest match. When you go for the longest match, you don't stop here. You keep going until you get to this. So this is the longest match. So the longest match, there is only one matching regular expression, and this will get taken as an identifier, a variable name. Okay. So now we have been assuming that in order to represent keywords and identifiers, you should have a regular expression for each keyword. So this is one way of doing it. That for each keyword will have its own regular expression, and that regular expression will correspond to a branch in the NFA that will get built. So as we have on the board, this is a branch that corresponds to a regular expression. This is another branch, and so forth. So there is another approach to recognizing keywords, which is instead of implementing them as separate regular expressions, we can recognize them as identifiers, and then whenever we recognize an identifier, we check if that identifier is a keyword or not. So the idea here is to get rid of all of these states, and just recognize the keywords as identifiers. But for every identifier, you do some kind of checking. You have to check it in a certain table. And that table will have to have what? It will have to have all the keywords in it. So there will be a keyword table. Keyword table, and that keyword table will have all the keywords in it: if, else, new, for, while, etc. It has all the keywords in it, and whenever you match an identifier, you check it in the keyword table and see if it's there. If it's there, it's a keyword. If it's not there, then it's a regular identifier. So now, in order for this to be efficient, how do you think we should be implementing this keyword table?
Hash table.
Hash table, yeah, exactly. The hash table is just the perfect data structure for implementing this keyword table. In fact, you can easily do perfect hashing. This is an example where you can do perfect hashing. Why can you do perfect hashing easily here?
Because you know exactly what's going to be in it.
You know exactly the number of entries that you will have in this table, and there aren't very many of them. In a typical language, the number of keywords is very limited, and you know exactly how many keywords. So if the language has 50 keywords, then 50 is all what you need to have in this table. So hash table is the best implementation for this, and you can do perfect hashing. And if you can do perfect hashing, because the number of entries is limited, this means that searching for the lexeme that you have matched, searching for this in the keyword table is going to take what? What will be the asymptotic complexity for the search operation in this case?
Constant?
Constant, yeah, it's going to be O of 1. So it's going to be O of 1 constant time search. But now the question is, now let's try to understand the trade-offs here, the advantages and disadvantages of implementing keywords as separate REs or separate branches in the NFA, as opposed to implementing keywords as identifiers and then checking in the keyword table. So now, from space point of view, obviously we have a disadvantage here. When we are implementing these as separate REs, then we will have a lot more states in the NFA and in the corresponding DFA that this NFA will get converted to. So that the resulting DFA will be much bigger when we have keywords represented as REs or NFAs. So there will be a lot more states, a lot more space used that we need to use. Now, in terms of speed, so here with the hash table implementation, we will have to perform this checking. So we will have for every lexeme that matches an identifier, we will have to do the check in the table. And in most cases, will the result be found or not found? Not found, because in a typical program, you have more variable names than you have keywords, right? So there will be, most lexemes are going to be variable names or function names. So they're going to be identifiers. They're not going to be keywords. So it's like, for every 100 checks that you do, only 5 of them are going to hit in the keyword table. So you will be doing the checking. That checking will be an overhead, right? Even though it's O of 1, but it still takes time. It's not 0 time. So it will take some time. And the question is, this checking in the keyword table, will this be done at compile time or while building a compiler?
Compile time.
So we will have to do it when we are actually compiling a program. So this is something that will affect the compile speed. Because when we are compiling the program, not when we are building, not here. It's not going to be done here when we are building the compiler. It's going to be done when we are compiling an actual million-line application. And in this million line or millions of lines, there will be millions or hundreds of thousands of variable names, and we will have to do this check, and most of them are not keywords. So there is an overhead here, although it's not, it's not too bad, because after all, it's constant time. It's O of 1. But there is an overhead, only to save us some, to reduce the number of states in the view. Any questions on this? Questions? Is it clear what the trade-offs are and what the two different approaches are? Okay. So is it clear to you now how we do scanners? So in fact, all of this is done for you in practice. There are tools that do this, but there are people who write this by hand. So the scanner is easy enough to write by hand, unlike the parser. As we will see when we get to parsing, parsing is much more complicated than scanning. So even though there are tools that do this for you, but if you have to do it, if you have to do all of this by hand, it's not that bad. It's non-trivial, but it's not, as difficult as building a parser. And in next time, we will be again going through more details about how this code generation is done, how the scanner is getting generated. Given a DFA, how do you generate code for that DFA? So this is something that we will be covering next time. And there will be two approaches, a table-driven approach and a direct coded approach. So you can just put the DFA in a table, and the table here means a two-dimensional array. You always keep in mind that the DFA is just a two-dimensional array in which the rows are the states and the columns are what?
Symbols.
The symbols of the alphabet. So A, B, C, 2, etc. So we will talk about this in greater detail tomorrow, next time, I mean. And I think that will be the last lecture on scanning.